Okay, guys. Let's go over what we talked about it. The intention, we posted this, I don't know, this page is from this book. She's gonna take it out of the website, tonight. If you need to copy it, if you need to download it, do it. She's gonna take it, off the website because I don't want to keep this one over there. I'll tell you why. If you need to copy it, if you need to get any copy, just go to before end of the night. 12 midnight, we're gonna go over. This is what we talk. We're gonna talk about it. I think the title is called. I think they call it single phase. Per phase analysis. We're going to get into per phase analysis for the three-phase transformer. We said delta delta and delta and y they're easy. We treat them like a single phase transformer. I'm going to draw the single phase diagram of that one later. I started with the delta y. We have a three-phase transformer. Is connected as a delta y. You can see here, and the transfer ratio for in the middle, VAB is going to be the square root of 3 with the angle of 30 times this voltage here. So from these two equations, I derived this one. We said the VAN in the secondary is square root of 3K with the angle of 30 times VAN in the primary. And these are phasors. These are phasors. These are not the scholar, they are phasors. Now we said the same way we can say VBN is equal to the square root of 3K with an angle of 30, VBN, and VCN is equal to the square root of 3K with an angle of 30, VCN. After that, we got to the current. So basically, we want to see what's the relation between this current and that current. If you look at here, I can say IA is equal to IAB minus ICA. Right? IAB minus ICA. But let's look at here. IAB is going to be related to IA. ICA is going to be related to IC, right? This is the IB and IC. So IAB is equal to, is a transformer. N1 IAB is equal to N2 IA. So it's going to be N2 over N1 IA minus N2 over N1 IB. Right? Now I see. Which one is it? What is this one? I see. IA minus IC. So I replace it over there. So basically, sorry, don't write it. Don't write it. Don't write it. Don't write it. I'm going to replace it. How much is the IAB? I'm going to replace it with the IA. IAB is the phase voltage here, right? So it's going to be related to this IA. So IAB is equal to is the phase current. That one is the line current. You said in the delta connection, the line current is the square root of the 3 of the phase current. Line current. I'm putting it right. We say the line current IA is equal to the square root of 3 I fade with the minus 30 angle. So basically IAB is going to be IA. I don't know what you guys are talking about. Ask me if you're not interested. If you want to talk, please leave the class. If it's related to the course, ask me, I'll talk. I will be very happy to talk about it. If you're going to talk about what DGP, saying joke, please leave the class. You are a grown man and woman. I shouldn't come back. It should be kind of shameful for me to tell you guys with your age to not talk. Now, we'll go to the now we'll replace the ICA. What is the ICA? Let's look at it here. We need to relate ICA to IA. I want to relate it to the IA. Let's draw the diagram so that we can understand it better. Let's say this is the IAB, right? This is the IBC, and this is the ICA, right? And now we know IA is going to be here. This is the IA, and this is the IB, and this is the IC. This one should be correct. IC. This is 30. Now, I want to find the relation between IA and IA. So we said this current is equal to this one minus this one. IAB easily I can replace it with IA. ICA easily I can replace it with the this one. This is the IA. This is the IB, and this is the IC. This is the IC. What is IA minus IC? It's going to be like this. This is the minus IC. This is the IA minus IC. This angle is 30 degrees, right? How much is this? If this one is I, this one is the square root of 3I, right? So basically IA minus IC is going to be the square root of 3 times IA, but 30 degrees behind, right? It should be this. So, just this is the IA, I'm going to write it here. This one is equal to the square root of 3 with a minus 30 degree times I, times I. So, look at this vector, it is 30 degree behind, right? And times by square root of 3 is going to be this. So now, we find this one. Say IA, let's summarize. IA is equal to N2 over N1 is the K. We call it K. It's going to be the square root of 3 K with minus 30 times I. See that here? This is the ratio for the voltage, square root of 3k to the 30. But we need to find the relation. If we call this one, for example, like, K1, let's say K1, so IA is going to be 1 over square root of 3k so when we had a transformer, single phase transformer, look at it here. If we have a transformer like this, N1, N2, which we call N1 over N2 is equal to K, we say V1 over V2 is equal to K. Or we can say V1 and V2. V1 is equal to K V2. And we said I1, I2. N1, I1 is equal to, we said I1 over I2 is equal to N2 over N1. So N2 over, so basically this is 1 over K. Basically, I1 is 1 over K, I2. Look at here, now compare this one, see? This is a V1 equal to something times V2, right? Here, look at it. This part, if we put 1 over this, look at here. If this is a transformer ratio, right? 1 over this is this number, right? No, sorry. The only difference is the angle, So the scalar part, like exactly single phase transformer. The square root of 3k here for the voltage conversion, 1 over the square root of 3k for the current conversion. But the angles, they are the same. See, 30 degree, 30 degree. So this is how you convert the voltage and current from primary to secondary and secondary to the primary. Now, if you want to find ID, IC, the same thing. And IC is going to be and by the way, in the last class I said e to the power of j pi over 6, this is 1 over 30. These are the same thing. The meaning obviously they are the same. If we see in the last class, no, e to the power of j pi over 6 is equal to 1 with 30. You guys, you kind of mix me off, I cannot even talk anymore, And okay. Now we know how to convert the voltage and current from the primary and secondary. How about the impedance transfer? How about impedance transfer? We want to see if you have something in the secondary, if you are going to bring it to the primary. Here was easy. If I had for example, impedance here. If I want to bring it here, we said, okay, if this is a Z, here, Z2, let's call it Z2. Z1 is going to be N1 over N2 to the power of 2, Z2. That was how we did it in the for the single phase transformer. Now let's look at it, for delta and Y, everything is exactly like single phase transformer. Nothing is different. But for the delta Y and Y delta, they are a little bit different. We are going through those kind of things. Let's say now we have I want to see an impedance in the primary is equivalent to how much of in secondary, right? We have, for example, Z1 is a VAN over IA, right? You put the equivalent circuit of this one, right? Like this. Right? So the input impedance is this voltage divided by this current, right? VAN divided by IA, right? Now I call this one Z1. I want to know if this one is going to go here. What's the relation between these two? So let's put it this way. VAN. to be VAN over square root of 3K. Sorry, it's going to be VAN over 330, right? So how about IA? IA is going to be, what is this? This is a Z2, right? The impedance in the secondary, right? So it's going to be double check this one. Let me make sure this is
I think the angle might be the bottom.
angle is okay.
The bottom angle 30.
No, this is correct. These two are very cancel each other. These two are very cancel each other, right? It's going to be this one times this, right? This one times 30 times minus 30 is going to add them together, right? It's going to be 0. So let me just double check this to make sure that you define the book define the change in the no, that's correct. Yeah, that's this one define this square root of k. The definition of this one is different. This is correct. So you can transfer the impedance from the secondary of a star connection to the primary of a delta connection with this equation.
So you're referring the primary to the secondary? Is that what you're doing right now? And the impedance transfer from primary to secondary, right?
Right. Primary. We can go either from primary to secondary. This equation you get. I'm saying Z1 is equal to 1 over 3K2 Z2. Or you can say Z2 is equal to 3K2, sorry, K to the power of 2 Z1. You can go either way, you know. If you want to go from this side to that side or from that side to this side, you use this equation. So this is the impedance transfer for the delta Y connection. So if you do the same thing for Y delta, let me summarize it in a table. If you do the same things for Y delta, you're going to end up with the same equation. I'm going to summarize it over there. No, I'm saying, when you have this one, like the circuit, let's call this one P, right? And this one was an N1, N2, right? If you want to bring this one here, how do you bring it here? If you want to bring this one to this side, it will be equal to this one, right? V2 times N1 over N2 to the power, right? You can replace this circuit with this circuit, right? If you had it this way, if you want to bring it here, it would be like this. And this one would be N2 over N1, whatever. Right? Just here I'm saying if you're going to transfer the impedance from a secondary, you have, for example, 2 ohm in your secondary. You want to bring it to the primary. How you can bring it? This is you use this equation. But be careful. K, I defined it here It was a single phase transformation. When I'm saying N1 over N2, if I would have defined it based on the line to line, this tree is going to go away. Now when you read this note, you see a square root of 3 different between here and what is in the note. Don't get just confused. You know what I'm saying? He defined a new parameter here, K1. He defined K1 this. You know what I'm saying? It's defining this one. You know, just I'm saying, be careful. You know, if you are reading this note, don't get confused. This is exactly what I'm saying here. Now, let's summarize this one. If we have a delta y, which I already went through, and again, when you read this book, it talks about the positive sequence, negative sequence, and zero sequence. Forget the negative sequence and zero sequence. No, we're not going to talk about that. Positive sequence is A, B, C. Negative sequence is A, C, B. And zero sequence, there is a kind of definition for it. I don't want to talk about it. So when, for example, when you see this table here, there is for positive sequence and there is for negative sequence. Forget the negative sequence. You know, you don't have to think about the negative sequence. So if you have a delta y, and we have y delta. Delta y, the ratio was this one was the square root of 3 k e to the power of j pi over 6 or I put it with an angle of 30. As I say, either way they're the same mean. If you have a y delta, again think about it. Y delta is like this. You have this one. Again, this one is N1. This is N2. Sorry, I was wrong. If this one is N1, N2, again K is, what did I define it? N2 over N1? N2 over N1. Now, for Y delta is going to be a square root of 3. It's going to be K over I'm going to use this equation later to make it easy for drawing the y delta and those kind of things. These are the transformer ratio. So if you remember here, if you are going to get the transfer ratio for the current, what should you do? Or to get the, this is for the voltage, right? You say V2 is equal to this one times V1, right? Or V2 is equal to this one times V1, right? If you want the current, how about that? So it's going to be 1 over this, but don't change the angle. 1 over this, don't change the angle. You know, just keep in mind, you're not changing the angle. Be careful, okay? So look at it here. See, we have the same thing here. We didn't change the angle, right? Now, I'm going to summarize all the circuits for the y delta, and y delta and delta y for a single phase diagram. You know, we're going to go with a single phase or per phase diagram, you know, based on what we talked here. So per phase diagram. We start with the Y1. Y1 connection. So we're going to see how we are going to write the per phase diagram for it. So basically we have this. Let's see what is this. Let's look at it. So remember, every transformer, every single phase transformer, we had this. I can put the RC, if you want, you can put the RC here also. But let's say this is the R1, L1, and Ln. These are Ln. And this is the ideal transformer. Look at here. This is the ideal transformer. Remember when we had the transformer, it was like this. Right? This is what we had from before, right? So just I put every phase, I draw every phase like that. This is the phase A with this one. This is the phase B. This is the A, C, D, and this is the A, B, C. So phase A here. Yes. This phase B. See, this is the resistance of the wire, and this is the leakage inductance. You know what I'm saying, for phase B. Resistance of the wire for phase C and the leakage inductance for phase C. These are the magnetization impedance for phase B and phase C, right? So we have this system. Instead of solving everything together, what I'm going to do, I'm going to come with a single phase equivalent circuit of this system. To do that, I can do this. Just I'm going to go draw the phase A here, right? And I assume there is a neutral. Let me put it with the other color. Let me put it with the other color. I assume there is a fake, neutral wire here. Yes.
On the right side for the Y connection, is it supposed to be N1 or N2? Or do they have like the same?
Oh, this one is N, yes. This is secondary thing.
What about the polarity? Is there a reason that you do the polarity like you did? Got it.
Yeah, yes. I'm wrong. Thank you. Now, see guys, I can break this circuit into three parts. One here, and one here, right? If I have only this part, there is an IA coming here, going this way, right? Think about it. This red wire is going to be common for all three circuits, right? If I have this circuit, the IC is coming here, going this way, right? If I have this circuit, it's going to be IB coming here, going this way. So basically, at the end, what current is going through this red wire? IA plus IB plus IC, right? How much is the IA plus IB plus IC? 0. So basically, when I put it here as a single phase, you see, hey, there is a current in this phase, in this wire. Don't be surprised. So this current is not carrying any current, but I'm doing it only one phase, right? When I put all three phases together, the current in this wire will be how much? Will be 0. So basically this one, a single phase would be as simple as this. And these are the voltages here, they are the phase voltages. What voltage we have here? VAN. Be careful. VAN. This is the N. Right? And this is the IA. On this side, let's call this one VA. It's going to be VAN. And this is the IA. So I'm going to solve this one. When I get to the problem to solve it, I'm going to solve this one. And whatever, for example, if I need IB over there, I said, okay, I calculate IA, just shifted minus 120 degrees. Or if I need IC, the same thing. If I need a VAB, I said I have a VAN here, right? If I need VAB, it's going to be line voltage, the square root of 3 times this one, and add here the angle, right? So basically, solving this circuit is going to give me all I need. Whatever else you ask me, I can calculate based on the result of this one. So this is very simple. This is, as I said, this is exactly like the single phase transformer. You know, we talked about it for a Y-Y connection. Now, let's go for delta connection. Delta connection also is easy. Let's do that one. So the next one would be delta delta. This is for the YY. We use this circuit for the YY. Now we'll go to the delta delta. I'm going to draw the same thing here with the delta. You got it here? I'm going to do this. A. This is the B. And this is the C. Let's call this one again R1, L1, and LL1, and LM. And let's put the dots here. So again here, this is the R1, LL1, LM. LM, R1, LL1, this is the N1, N1, and N1. Right? This is the primary. Primary of transformer is the delta, right? There is a resistor like it, because every phase is one transformer, right? And there is a secondary. Secondary is delta delta. Again, I have this one. This is the IA, right? And this is the IAB, and this is the IBC, and this is the ICA, right? Now, this is the A, B, and and C. This is the IA, IB, IC. Right, and this one is going to be this is the IAD, IEC, and IC. This is a delta-delta connection. I transfer all the impedances to the primary, okay? All the impedances are, I draw them in the primary. Now we want to see what's the per phase for the circuit. What does it mean per phase again here? If I'm going to go per phase, is like I come up with a kind of equivalent circuit here, right? Something like that. I'm going to make it, and the same thing over there. Right? To make it perfect. You know, I'll convert this one to a star, I'll convert this one to the star, basically become like that, right? But keep in mind, to convert this one to the star, all the impedances is going to be divided by 3, right? This is a delta. I'm converting it to the star. So we said Z star is equal to Z delta over 3, right? So basically, if I'm going to redraw this one, so this one is going to be R1 over 3, LL1 over 3, LM over 3, and N1 something, right? N1 either time to the square root of 3 or something, you know? That one doesn't matter. Why? Come here. This is N1 and this is N2. N2, N2, and N2. So when we'll come here, we are going to convert this one also to the star, right? Do I have any impedance here to be worried about it? No, because I put all the impedances on my primary, right? So if here, for example, I don't know what's going to happen. For example, when I convert this one to the star, for example, let's say this one is going to get N1 over a square root of 3, right? Because this N somehow represents the voltage, right? The same thing is going to happen here, right? No impedance, but for here also N2 is going to get divided by square root of 3. If both of them, they are divided by the same number, you can assume that they didn't divide by any number, right? The transformer ratio is not going to change at all. So here I can draw the single phase now. The single phase is going to be like this. The single phase is going to be like this. This one is going to be R1 over 3, LL1 over 3, LM over 3. But here N1 and N2, they're going to stay the same. Why? Why? Because whatever happens here is going to happen here also, right? For example, this one will be N1 over a square root of 3. This one would be N2 over a square root of 3 also, right? Both of them, they are divided by a square root of 3. So I'll ignore this square root. N1, N2. This current is IA. This current is this IA. This voltage is VAN. See, N will be this point. This voltage would be VAN. Basically, N is this. So again, it's like a single phase transformer, exactly what we have for a single phase transformer. The only thing is R and L, they are going to be divided by 3. When you draw the single phase system, R and L, they are going to get divided by 3. Because it was a delta, we converted to the star. And we came up, for the per phase, circuit. Clear? Now let's get to the other one, the delta Y and Y delta. me write it in the therefore. So basically, again, this part is going to be the same. I'm going to have the same circuit here. My primary is delta, right? I'm going to do it this way. So this is A, this is B, and this is C. This is the R1, exactly what we have over there. LL1, LM, this is A, for example, this is the N1, this is B, this is the N2, sorry, N1, LM, LL1, R1, LM, R1, LL1, and a dot and one. This is the IA, this is the IC, IB, right? This is the delta. We're going to delta it, right? Just as exactly as the same thing we have over there. Now I'm going to put the Y side. Y side is going to be like this. This is the A, this is the B, and this is the C. This is the N2, and this is the IA, IB, IC. Let's call this point N. This is the A, B, C. Now, look at it. I want to draw a single phase circuit for this system. So if I want to draw the single phase system, I should convert this one to what? To a star, right? If I convert this one to a star, what is going to happen to the impedances? If I convert this one like this, let's call this point N, Bn. So basically the impedances, they are going to be divided by 3, right? So it's going to be like this. A single phase circuit is going to be R1 over 3, LL1 over 3, LM over 3. Now the ratio. The ratio is very important. Here is going to be VAN, right? This is the N, right? The fake N, there is no real N, right? This is the VAN. This is the IA. This is the VAN. Can someone tell me what's the ratio here? Let's put the dots here. Can someone tell me what's the ratio here? What is the ratio? What is the ratio? N1 over 3. Let's call let's call N2 over N1. Okay. I made it a little bit easier. Now Now tell me. Huh? Then we what? N1, N1? No. What would be?
1 over 3K.
1 over 3K. What goes?
3K.
I was going to write here first. I said let's not grade, you know. If you have a delta y, what was the ratio? 3k e to the power of j 5 over 6, right? So basically, this transformer is going to be root 3 over that root 3k. See, the transformer with a complex ratio now. There in reality there is no such a transformer. You know, these are all mathematical models. You know, or just solving the problem. There is nothing like that, but this is to solve the problem. Now we will go through the example. We'll see when I'm going to calculate the current here. I'm not worrying which one is the head, which one is the back. You know, whatever. I'm going to start to solve this equation like this, and I use this one to convert the value from right side to the left side to the right side. You know what I'm saying? So this one is going to make it very simple for us now. I solve this one like a single phase transformer. The only thing is the ratio is this number. The ratio is this number. Get it? So if you look at the book also draw it this way. I'm not ready here. This one also you can draw it this way. You can say what is this one? That's it. Look. Basically here, so let's call this one B prime and I prime. So that you can forget this one, right? This is not no more, you know, 8 e to the power of j or I don't know, that j5 over 6. So basically, you can solve this one like a regular transformer. This is a transformer ratio. When you need this number, just times by e to the power of j to the power of j pi over 6. So let me make sure that's what it is like that. So this is the equivalent circuit per phase for delta Y connection. Per phase for delta Y connection. Now let's go for the next one. It's going to be Y delta, right? Y delta. So I'm going to arrange this one, just keep this one here. Y delta, right? So we are going to have this. Y delta is going to be like this. ID, and this is the N, right? And let's put a dot here, and dot. This is the primary, right? And the secondary is the delta. This one is A, this one is B, this one is C, IA, IB, IC, N2, 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 IAB, IBC, and IC. So I'm going to draw the per phase here. Again, here it needs to become a kind of fake stop, right? Now I can go one phase to one phase, right? Do I need to divide this one by square by 3 or not? Am I converting this side to anything? No. No. So basically it's going to stay the same. R1, L1, L2. No change, right? Here when I did here, I divide them by 3. Why? Because I converted to stop, right? I divided by 3. But here I'm not converting it to anything. Basically, the circuit is going to be like this. The circuit is going to be like this. What is the transformer ratio here? This one, right? This one means, if here is one term, this side is k over the square root of 3 times that, right? This side is this many numbers. Or you can put it this way here. This one is equivalent to this one. You can put it this way. You can deal with that. You can solve this one like a regular single phase transformer. When you need this value, if you are going to go from here to here, you should time it by this, right? If you are going to go from here to here, you should divide it by this. Be careful, Going this way or going this way means 30 degree. Adding or subtracting, right? Just be careful about that. So this is all about the three-phase circuit. Three-phase transformer. There is one more topic I want to talk about it and finish the three-phase transformer. And if we have time, I'm going to solve one example of it. about the, we call it open delta. Or they call it V connection. See, right up to here we had a delta Y, Y delta, delta delta, Y Y. Let's see what's the V connection. Let's see what's the V connection. Let's assume you had a delta delta. They call it either open delta or VV connection. Let's say you had a delta delta transfer. And you have a load. Right? We have this delta delta connection, and we have a three-phase load. We are supporting this load. Okay? Let's call this current IA, IE, and this one has a power factor of cosine, right? Correct? Good. Let's think about it, you know. If I lose this one, somehow this is a three single phase transformer, right? This is a three single phase transformer, right? Let's say that phase, the transformer somehow is back, is gone. I want to see what's the relation for the power and those kind of things compared to the full delta there. I'm going to put this one in the other color. So basically, initially was a delta delta. Something happened. So we had a three single phase transformer, right? So something happened. One of these transformers is not working anymore. We have to take it off the circuit. When I calculate the equation, I'll tell you what's the advantage of this circuit. We'll talk about that. Well, let's go through the equation first. I'm going to replace this load to make it easier for you guys. I'm going to replace this load with a star connection of this load. So I have a load here. I have a load here, like this. And the power factor is cosine, right? Basically, this one is coming inside. Let's call this point N. And we know this is A, this is B, this is C, right? Let's draw the phasor diagram from the load side first. So I'm going to calculate this. Let's think about this. If the nominal current of this one is I, this point, I'm saying the value. For example, this transformer can handle 100 amps or 200 amps. The nominal current of this transformer is I, the value. And this voltage is V, for example. These are the nominal values. For example, you say 230 volt transformer to, I don't know, 500 volt, right? So these are the nominal value of this transformer, so we can calculate the power. If let's say delta condition, my power has to be 3 VI cosine phi. Is it correct? If this winding is all the same, right? How much power I'm going to have here? VI cosine phi, right? VI cosine phi, VI cosine phi. If I have 3 windings, if I have delta delta, so the total power would have been 3 VI cosine phi, right? Correct? V and I, they are the phase values. Careful, okay? Now, the red winding is gone. I want to see how much power I can have right now. Originally, when I had the 3-phase transformers, I'm going to ask you this question. Let's say it was 300 kilowatt. What's your guess when I have 2 windings? 200 kilowatt. It looks very kind of a reasonable guess. But it's not correct. We'll go through it why. But a very good guess. Myself also, the first guess would be, okay, I had 3, 1 is gone. So now it's going to be 2/3, right? 200 kilowatt. But let's go through the equation why is not. Let's look at it, why is not. So, I'm going to come here to calculate this voltage now, this VAB, right? Look at here, VAB. This load is the balanced 3-phase load, right? Balanced 3-phase load here. This VAB here is a line voltage here, right? Line voltage. Is it correct? Let's draw the VAB. Oh, before going there, we said this load is the 3-phase balance load with a power factor of cosine phi, right? So basically, for example, IA is a lagging, assume lagging. So IA is going to be here, IB is going to be here, right? And IC is going to be here, right? It's a 3-phase load, balance load, lagging power factor. So basically, we have a current is lagging phi degree with respect to the voltage, right? Now, I'm going to come calculate the power from this side. Look at here, forget that side. This side, I want to calculate this side, right? I want to see how much is this voltage, right? The current is staying the same, right? Let's look at the voltage here. The voltage, VAB. VAB is going to be like this. And how much is this angle? 30 degrees. Why did I plot the VAB? Can somebody tell me? Why did I plot the VAB? Look at here. I want to calculate how much power I have here, right? I want to know how much power I have here. How much is the current here? Current is IA, right? Current is IA. I need to know what is the voltage here, right? And what is the power factor, so basically I can calculate the power, right? For how about this one? I should calculate VCB. Look at here, the current is going this way. I should calculate VCB, right? Where is VCB? Let me draw the VBC first, right? VBC is going to be VB minus this is the VBC, right? And again, this is 30 meters. What is VCB? Look at here. Just look at here. Current is is the source. This is the source. Current is going from A. I said VAB, right? Current is going from C. I need to calculate VCB, right? So I have a VBC, so this is a VC. How much is this angle? 30 degree, right? How much is this angle? 30 minus phi, right? How much is this angle? 30 plus phi, right? So somebody tell me how much is the PAB. Now we are going to go VB. How much is the PAB? How much is the PAB? Look at this diagram and tell me how much is the PAB.
Root 3.
PAB, AB is the one phase, right? It's going to be voltage of AB times the current of AB times the cosine of whatever is the power factor. So it's going to be VAB, right? IA, right? These are the scalar, right? How much is the angle between VAB and IA? 30 plus 3. So it's going to be cosine of 30 plus 6. How much was the VAB? Nominal V. How much was IAB? In this case, IA and IAB is going to be the same. How much was the nominal current for this winding? R. Basically, this one is going to be VI cosine of phi plus 30. Right? I'm going to compare it with the top one over. Now tell me how much is the PCB? How much PCB? ECB times IC times 30 minus T, right? Basically, it's going to be VI cosine of 30 minus T. Yes.
For the diagram, oh wait, never mind.
Okay. So how much is the P in total now? It's going to be PAB plus PCB, right? Let's say PVB. Let's call it PVB. How much is the PVB in this case? It's going to be PAB plus PCB, right? If we calculate this one, it's going to be 2 VI cosine 30 cosine phi. Just add this together. Right? Now let's write it here. PVV over P delta delta is going to be 2 VI cosine 30 cosine phi over 3 VI cosine phi. This one, this one, this one, this one, this one, this one. So it's going to be 2 cosine 30. How much cosine 30 is the square root of 3 over 2, I believe, right? Right?
Yeah.
Yeah. So it's going to be, which this one I think is 58%. In the point, I believe it's either point 57 or point 58. So we said initially we expected to be 2/3, right? 2/3 means 66%, right? You can see it's a little bit less than 66%. Can you tell me when we can use this one? Do we use this connection at all? Almost no. Maybe 1%, 2%. why, when the 1%, 2% can happen?
If one of the transformers breaks down and you have to compensate for it,
If I want to take the transformer down, you say?
yeah, you have to compensate.
So why do I want to take the transformer down?
If there's a problem with it, if there's a problem.
No, that's exactly correct. Let's say, hey, there is a problem with one of the transformers, and I don't have a replacement for it, right? I have a two choice. So you think about it. We have a three single phase transformer here. One of them is not good. I have a two choice. Hey, load, I cannot give you it. Shut it down. Or I can say, hey, I can cover almost 60% of it, right? So this is the only case we use that doesn't fit immediately. But usually, in the power system, we try to not go for this kind of thing. We stay with it, does, and why. But if you are in a kind of emergency condition, we have to have a power, and one of the transformer is gone, and we don't have any spare, so we can use a DV connection. Basically, we can cover up to 58% of the load. Any questions? I'm going to go over one example. Those ones they want to leave, you can, because this one is going to go maybe to 6:30, So I want to cover one example on this single phase circuit we went through. This is not part of class anymore. This is like a discussion class. I'm going to go over one example. Any question? I'm going to go example 5.4 of this note. Just I want to explain it, we can work a little bit more on this. Do me one favor, Do what you did. Those ones are not great, keep it here. Those ones are great, take it over there. The one that are not great, keep it there. The one they are created, they are back there. The one they are created, they are back there. You can pick it up from there. Before we leave the class, we have the final next Thursday. Do you want to move it to next Tuesday after or not? Yes. So we will take the exam to Tuesday after we were supposed to have a midterm Thursday, but we'll transfer it to the next Tuesday after the Thursday. I don't know which day. Okay? Homework due would be until next Thursday. Yes. Next Thursday. And let them know the due date for the homework is next Thursday, and the midterm is put the date over there. I don't know what date it is. It's Tuesday after next Thursday. You have questions as well. On this particular class. So I'm going to go through one example on this. I believe we need to talk about this one a little bit. Last time we went through one example and we saw how much of pain was that one. Now let's look at this one. Example 5.4 it says we are giving a system involving a step up. A step up means, you know, the transformer secondary voltage is more than primary. You have a step up and a step down. A step up will basically bring the voltage up. A step down brings the voltage down. So you have a step up transformer, and this is the circuit diagram. And this transformer is delta 1, and here is the generator. We have a circuit like this. We have a generator connected to a transformer. This is like a where you generate power. You call it a power plant. This is like a power plant. You know, in power plant you have a generator, and you step up a voltage, send it to the transmission line, and transmission line is going to go, for example, to this city. You have to step it down. But we didn't show the rest of the circuit. We showed the part only in the power plant. Now, it said this one is a 3 single phase transformer, and each is specified by X1 is 0.21 ohm, and we call it K, is N2 over N1 is equal to 10. It said each generator phase is modeled by a Thevenin equivalent circuit. The transformer bank is delivering 100 megawatt. This load here is 100 megawatt with a power factor of how much? 0.9 lakh. So it says substation, you know, 220 kV. You have that one, 220 kV, and now it said find the primary current. Find the primary current, primary voltage line to line. Now see, if you look at here, I want to know IL, VLL here. I want it for this side. This is the primary. I want to find the primary current, primary voltage line to line, and three-phase complex power here. I want to know the SG. Complex power of the generator. I want to calculate complex power means to calculate P and Q of the generator. Basically, S generator is the P generator plus J Q generator, right? It's saying calculate P and Q for the generator, how much they are. This is part A. Part B says find the phase shift between the primary and secondary voltage. That's what it is, you know. That's not big deal. Now let's do this. We don't have the generator. So let's start solving this one. I'm going to make it easy for myself. I'm going to draw this thing per phase circuit, right? Generator is like this in general. Generator is like this. It's a Thevenin circuit, right? See, usually guys, we don't put it even R. R is very small compared to the. This is the one phase of generator. Every generator has a source and some impedance. This is the second phase. This is the third phase. In this example, here I can assume the generator is ideal, which means all these x's they are 0, or I can calculate the voltage here. You know what I'm saying? I cannot go calculate this value. You know, if you look at the book, they calculated this voltage. But myself, I assume the generator is ideal, so there is no x for generator. This x is for the transformer, right? There is no R. There is no R, there is no LM, right? Only there is the X. LM. There is only LM, right? I talked about it. It said when you are going to go with approximate model of the transformer, it said forget RC and LM, right? And even one more step down is forget the R. Just consider the LM, right? In this example, they give us only X value, right? Now I want to draw the per phase system. Here, how should I draw it? Let's go. There is no R. I'm going to use the note you have. It was R, X, LM, ideal transformer, right? So R is 0, forget it. Lm is 0, forget it. Just I'm going to put the x1 here, right? But this is delta, right? What should I do? Divide it by 3. Whatever is here, I should put a point J, 0.21 over 3, right? Yes.
Why do you find the per phase system?
Perfect is much easier to solve. Remember when we started the three-phase circuit, we said just draw the one single phase, solve that single phase, right? Instead of going through all three phases, you know, yeah, you can, if you have phase A, you can find whatever you want for the rest of the phases, right? So here we are going to have a transformer, right? What was the transformer ratio for this one? It was 1 to a square root of k, right? With the angle of how much? 30 degree, right? How much is the k here? 10. Basically, it's going to be 10 a square root of 3 with 30 degree, right? I have a transformer like this. Let's come here. So let me finish the generator. Generator here is like this. Yes, I said I assume the generator is ideal, right? I have like this for generator, right? I'm going to connect one phase of the generator here, right? So generator is going to be here. Let's call this point A. This is the A, right? And this is the N. Fake N. Why I'm saying fake N? Because this is delta, there is no N, right? Now, this one is going to be I line here. IA, right? This one is going to be IA. Let's go to the load side. Load side, I'm going to make my life easy. You didn't say anything, right? I can select anything I want. I'm going to select it as a star, right? I'm going to select that as a star. So basically, this one is going to be like this. How much is this voltage? Somebody tell me. How much is this voltage? 2300 divided by square root of 3, right? Because this is a line voltage. I said in a three-phase system, when they don't say anything, that's a line voltage, right? So this voltage is going to be, right? I need to select one reference for myself. I'm going to make this one as soon as easy. Right? How much is this current? Let's call it IA. How much is the IA? Can somebody tell me how much is the IA? IA is the line current here, or phase current, right? Because we assume this is the Y connection, right? Line and phase current, they are the same, right? We said P is equal to a square root of 3 IL VL cosine phi, right? Or we can say I is equal to P over a square root of VL cosine phi. So how much is the P here? 100 megawatt. The square root of 3 times how much is the VL? 2.3, right? How much is the cosine phi? 0.9. Can somebody calculate this number? I think it should be, I think it is 2279. 279. 279. Just double check it to make sure it's correct. This one was P, this is the VL, and this is the cosine phi, right? I calculated it. So how much is IA here? With how much angle? How much angle?
It's inverse cosine.
Minus cosine inverse 0.9, right? Minus cosine inverse 0.9. You know, I'm going to stop it here because the rest is very, very simple. So basically, it says how much is the VL to element, right? You know this voltage. Just bring it here, right? You write the KVL here. The rest is in the book, you know, you can read it. But you can write the KVL here. You calculate this voltage, right? let's say we calculate how much, I don't know, 1400 volt with some angle, right? Hold on, let me finish up. This is a 1400 volt, right? So how much is the line to line voltage? Whatever you calculate here, times square root of 3, right? Because this is a phase. You are asking here to calculate the line to line voltage, right? How much is the IF? Sorry, I line here. Just transfer this from here, right? And you know how to transfer this, you got the equation for that when I was teaching you. Just you bring it here, this is the IF. So, how much is the complex power of SG? Let's say we calculate this one, just I assume, if we calculate this one, IA is 100 with -5, for example, and VAN, for example, is 1400 with, for example, 5 dB, right? Let's say we calculate these numbers we have here. How much is the complex power here? I can calculate P and I can calculate Q, right? For the generator. How much is the P? How much is the power factor for this generator? Cosine of this one minus this one, right? So basically in this case it's going to be cosine 10, right? How much is the power for one phase, active power for one phase of this? Is a VI 100 times this times cosine phi. How much is the Q? VI sine phi, right? How much is the total S? 3P plus 3JQ, right? Because this is per phase we are following. 3P plus 3JQ is 630. Now, the reason I didn't write it down